So probably we can start. Okay. So from now on, there will be coding sessions, and the codes are all up in the GitHub, which I showed you. So first, how many of you have never touched PyTorch? Wonderful, 70 or 80%. How many of you were there in the online tutorial I gave? Okay. So it may be that you have never done a coding of your own in PyTorch, but there is nothing to be afraid about. I can safely assume all of you have experience with NumPy, right? So PyTorch is a library which is almost like NumPy with its own autograd engine, and the rest of the conceptual things are same. So when you write something like numpy.ndarray, there is a similar thing called torch tensor, and all the concepts like you do mathematical operations using numpy on the numpy arrays, you should just remember the dictionary. Numpy array corresponds to torch tensor, and everything else is similar. And wherever you have doubts, we will walk through together and try to resolve it together. The thing when I gave that online tutorial using some classification on PyTorch, there were 2-3 important points. That first, how to do array manipulation using PyTorch. There was a concept of building a custom data set, and there was how to define a model in PyTorch. So at that point of time, if you had followed, wonderful, you can still find that piece of code in the same GitHub space where I'm putting all the codes. If you didn't try it, maybe today evening you can try them. And since these are in GitHub, you can make your own fork and run everything on Colab, and these pieces of code should run out of the box. So the whole point of the first tutorial today is that all of you have done MNIST handwritten digits image classification. That's kind of a very elementary task you take up when you start learning a machine learning course. So we will just repeat the same exercise so that you know what's the statistical learning task. But what we will do, we will convert the image to a set where we will only take the pixels of the image where there is some entry, and that can be random. It's not the same. Each and every set of pixels are ignited always. So we will convert the image to a set, and we will try to learn how to do machine learning on sets, the concept we just talked in the previous session, and how to build a deep set from scratch. And again, try to classify images, essentially. Just that image won't be the regular grid, but instead a set. So we will see how to do that. And you can download the code in live. You do not need any PyTorch geometric or PyGlib for running this piece of code, Deepsets tutorial. So if you have PyTorch installed in your laptop, you can do that. Since there is good internet here, you can also open this piece of code in Colab and try to run in Colab. It should work. I hope people are familiar with Colab. Okay, so let's start. Okay, so first there is something, a bunch of usual imports like torch data, etc. You can blindly copy paste this piece of code. It's just that when you compute some function like a linear layer or something like an activation like softmax, they are inside this part of the code called torch.nn.functional. That's it. So you just should know. And now I can't change slides, but browse through here. This piece of code snippet of code really sets what's the hardware acceleration you're using. And if you have GPU, it should be CUDA. If you're doing on an ARM64 M1 or M2 Mac, that should be MPS. Otherwise, if it's an Intel, it should be CPU. So let's see. So what is our dataset X? You see, we just took some MNIST data, put it in some local folder called data, and just took something. Okay, so here is a matplotlib, the digits 3. What we will do here is that this is a 28 by 28 array. Most of the spaces are dark, which means they have pixel values zeros. The whole point of this exercise is that we will throw away all the places where there is a zero entry, and we'll only take the ignited pieces of cells and try to do machine learning on that. And hence, you just can't take a filter where you will scan through the whole image, covering up whole pixels, so that like the way a convolutional network tries to detect edges, we won't apply that method, but we will just try to see, given like an image like this, we will associate a coordinate to each piece of active cell here, so that we know what is the value sitting, the pixel value sitting in the cell, and what is the coordinate. That should be a sufficient information, and we can throw away all the zero pieces out of this data set. Okay, so that's a piece of data set with which we will try to do machine learning. And here it's pretty easy way to do it. You just try to see, here is a little piece of code snippet which says what is the cells where you have a value greater than 0. And since it's 28 by 28 images, we just normalize it with the size 28, so that each point has a kind of a coordinate between 0 and 1. So if you are trying to run the code, you should be able to produce the output of the first few cells. So if you're trying and failing, let me know you have failed. That will be something interesting to look into. Right. So argware means tell me the locations. So, okay, first before telling you on, okay, let me first tell you on the board. And so let's say you have an array, torch tensors, where you have numbers like 0, 1, 2, 0, 0, 5. So the torch.argware will return you the location where it's non-zero. Okay, and then in the, if you're doing a live coding, it should so if you're looking into a regular Jupyter notebook kind of thing, you can do this stuff and put a double question. And let me just activate the environment. Yeah. So it will return you a description of what the things does. I mean, for me, here in this piece of code, it also tells you kind of in short what it's doing. Okay, so the best way, if you're doing it on live in the notebook, just copy paste the part which you have question about, and just put a double question and press enter for the cell, and it will give you a whole description of what that piece of code is doing. So here also they always provide a working example code snippet, which you can copy paste in another new cell and you can play with it. So you can see that it's essentially trying to find out where the non-zero elements are, the location of the non-zero elements. I did it on like dividing by the total length is something like converting a 0 to 28 length scale from 0 to 1. That's the mapping. Otherwise, there is no other purpose for that. Okay. So please keep asking questions because I really want you to get in the depth of the codes and I want you to understand. So thank you for that. Now, when I gave you the first like online tutorial, I told you that in PyTorch, when you're dealing with the data sets, you just can't live with arrays and things like that. You want to make complicated data sets. You want to build your own custom data set. Now, here what we are trying to do, we were given a 28 by 28 image. We want to take only the cells which had some values. How we will do it? We will do it by one of the self-built custom functions, which I called transform 2D image to point cloud. So we will walk through how do we convert a 2D image to a set, which I call point cloud, so that each time you insert a 2D image of 20 by 28 by 28, it will convert it to a set of a point cloud. So let's look into this. But this, we have to do it inside something called a custom data set in PyTorch. And this is inherited from the inbuilt dataset class. So I can safely assume you have done Python coding where you know class inheritance. If that's not the case, we can discuss it in the evening sessions or something, but here I have to assume it, otherwise I can't go forward. Right, so to do that, see what I have done. I have done, I have written a function, which is the function belonging to that class, and it's taking a tuple. Why it's a tuple? Because when you have labeled data set, it always comes with the data and its label. So it makes a tuple. It takes input a tuple and returns you something like a dictionary. What it's doing, that it's taking the image array, finding out the values. So it's like wherever it's greater than 0, the corresponding values, and the argvar is just giving you the locations. Okay, so colon comma 0 giving you the x locations, colon comma 1, it's a 2D image. So these are the only 2 dimensions. And this is giving you the coordinates in the x direction, comma 0, giving the coordinates in the y direction. Both the coordinates, it was 0 to 28. I have normalized it down to 0 to 1. That's why the division here. And then we are combining all the 3 information, the x coordinate, y coordinate, and the pixel value into one tuple. So that's the information for each ignited coordinate on that image 3, which we had. And we are clubbing them together. And what we are doing is that we call it a point vector. The image already had a label. And then the sequence length gives you how many non-zero pixels were there in that images. We need that information, as you will see. And this is the thing which converts, this is the code function snippet which converts a 2D image into a point cloud set. So we are just stacking them all together. Okay, and in PyTorch custom dataset, there are 2 pieces required. Len, it's an inbuilt function. It will give you that given like the raw images, how many total number of images. So when you call this custom dataset, if the number is less than whatever len is given, it will give you that number. So instead of len self point cloud dataset, you had written 10, then the total data size would have been always 10. So remember this fact. And the get item returns you each instance of the dataset. Okay, so there was a list of self point cloud dataset, which was just a list, and that get item will return you the ith element from this array. So Are you people trying it on live or not? You are? So give it a try. Just try to execute this piece of code and see, because it's important you grasp the main concepts, what's going on. So here, now that the raw images, the MNIST images were stored inside this folder .data, I created the custom dataset from the raw image dataset, which I call point cloud dataset. And here you see, if I take the 20th element, the counting starts from 0. So what is the 20th element of this point cloud dataset? So we have a set which was given point. It was each element had 3 features: the x coordinate, the y coordinate, and the pixel value. The corresponding label, it was an image of 9, and the sequence length. So out of 28 cross 28, there were 109 number of pixels which were used to build this image of 9. That's what this data set is meaning. So we will visualize that. So I have written another function which will, earlier you had a raw image in matplotlib, you plotted it, plot.imshow, it gave you an image. But now you're dealing with a point cloud data and you have less intuition about that point cloud data. So this visualize samples is a code snippet which converts the point cloud data into image and shows you what point cloud you're looking into. So this is like we took this piece of data, right? The 20th element, it's like a set. And here we just plotted it. So now you see you have just bunch of dots. And these are only where you had some ignited pixels. And it had converted to the image of 9 into a point cloud. So this is the set representation of the same image. Okay, is this clear what we are trying to do? Anyone who is not following the arguments, please stop me immediately. I really want you to understand what's going on. Once we have done this, there are 2 important pieces, conceptual concepts needed to be kept in mind. When you know the fact that when we do machine learning, we use something called mini batch. How many of you are not familiar with mini batching of the data? Some of you, okay, never mind. So if, let's say you have a large training data and so if you had a neural network function and each time you give it one data and it's giving you one output and you're doing a back propagation, there were some weights here and you're updating the weights through some back propagation you should identify this equation is that this is the gradient descent method. Now, in real life data, if you don't put a chunk of data together to a neural network, it's computationally inefficient, as well as it should have large statistical fluctuation. So to overcome these 2, let's say, a problem, the thing we use is that we stack together few instances of data together, form a mini batch, so that if there are some systematic, like some statistical fluctuation in the data, that will be removed by clubbing more and more data together, as well as when you're doing some training on GPU or something, then you put this whole chunk together to the GPU so that the computation on all this set of data will happen together. So that's why you always train on mini batches of data. Let's say if you have a training samples 1,000, then you don't train one by one on each of these 1,000 elements together. You say make a batch size of 10. That means you will divide the 1,000 size data set into 100 pieces where each piece clubs 10 instances of data together. and then it feeds the neural network this 100 pieces of data, and this it will computationally that the backpropagation will happen on these 100 segments, so it will be faster, and also this 10 a piece of 10 will have lesser fluctuation from the real data. It will have more statistical expressibility, so that's why you use the concept of mini batching. You must have used it when you were doing some, say, handwritten digit classification on MNIST data. And these arguments are independent of PyTorch TensorFlow JAX. These are just machine learning concepts. Okay. Yeah. No, where did you get it has to be power of 2? Are you mixing it with the kernel sizes with size of? No, I'm. No, why? It's usually on GitHub, whatever for what data set? There is no a priori reason why the batch size has to be power of 2. Elam, do you know anything such statement? But why? Because someone else did and they copied the code? No. Yeah, but I don't think mathematically there is a reason why a batch size has to be power of 2. There's no such reason. Even if it's like the power of a GPU is like whether you have a 32 GB GPU size or whatever, the RAM of the GPU. Huh? The thumb rule is that if you can load a chunk of data in your GPU and it can access the forward computation, if the memory allows you, then just try whatever gives you like efficient time to do one epoch of training. That it shouldn't clot your GPU, but you still can load a chunk of data. Okay. If you have a large training data set, no, because when the back propagation will happen, it will average over all possible mini batches and then only happen. Okay, so if you have truly a large data set, which, sorry? The batch, so hyperparameter comes with the formation of the architecture. So batch size is not related to that. This parameter is important to ensure you have the right chunk size to load on the GPU so that the GPU doesn't get clogged, but still you can do efficiently the training. Yes. So yeah, you load them in mini batches, collect the output, and then you're averaging so that you really did the back propagation by clubbing the data from the whole training data. For each batch, the gradients are updated. Which one? For each mini batch, the gradients are updated. You can do that. Like, okay, so a mini batch should be like a smaller representation of the data. In the whole epoch, for each mini batch, the gradients are updated. That's what you're asking. The gradients don't have that much. I think if you really don't have very large data and you do back propagation after each training on each mini batch, then you might introduce some instability. Yeah. So the best practice. The difference between this stochastic batch and mini batch is basically. Right. So for me, at least in my experience, the best practice is that you average by clubbing the information from all the batches so that you have the one epoch on the whole training data set, and then you do a backpropagation that is statistically like less fluctuation prone.
That is normal batch update. Like essentially, when you're calculating the gradient, you're calculating the gradient over the whole training set.
Right.
It's basically same as that. But when you say mini batch, you calculate the gradient on each mini batch and then update the gradient of the.
But you combine this information like.
Yeah, I mean, it is iterative.
Yeah. It's one follows the other, right? Yeah. Okay. Yeah.
Also, if we have a smaller batch, then it won't be representative of my larger data.
Yeah, it's statistically not the same. If you take a normalized distribution from the whole data set and from a mini batch, they might look different.
If I have a smaller amount of data, I should usually use a bigger batch.
I mean, if you have a smaller data set, then you can have the whole data you can put up in your GPU and train it once. Then you don't need to slice in mini batches at all.
If I have a larger data set, then
you have to split in mini batches.
relatively how much?
That's the hyperparameter of the training which you need to optimize. Yeah. We will see that. So right now I didn't talk about it. I didn't talk about the training. I'm just trying to tell you that we have to define mini batches and how to do it technically. Because when you were dealing with images, all the images had same size and you could have stacked them together. When you are having point cloud, then each instances of data have different number of points. And there you need to come up with a strategy that when there is a variable sizes of data, how to stack them together. Yeah, sequence length. An image of 3 and image of 9 can have different number of ignited points, so different sequence lengths, and how to club them together. Yeah, just that. Why don't you wait until we reach that part? Okay. So here, the concept I wanted to tell you that when you have different elements with different sequence lengths, you have to create a notion of zero padding by creating a vector where you take the maximum length from the sequence and then just fill the rest of them by zero padding. So here what I showed you is that data list is a list of data with different sequence lengths. Here you have to figure out what is the maximum sequence length, and then you just create an array with all elements 0 and copy the rest of the data. So this is the batch function. What is doing is that efficiently zero padding the rest of the elements and keeping the sequence length for each instance to the maximum length coming in a mini batch. Okay. And you pass it to a data loader. So just, yeah. So once you have the data loader, then you can iter over the data loader and create and can access each mini batch. So if you run this piece of code, you will get that the chunk. I have named it just to emphasize that it's not one instance of data, but depending on the batch size, you will get a chunk of data. And there is this keyword argument called collect function, which is the create batch function, which I wrote above. So it will just take all these 5 instances of data sets together, merge them, and create the batch. Now, conceptually, this is what I once mentioned in the first talk that how to build a permutation equivariant layer on a set. And if you read the original 2017 paper, this is the formula which is given as a permutation equivariant layer. We will try to understand this formula. It's important here. So in the computer science notation, first, let's think that gamma and lambda are just numbers. And let's take a set of 3 elements, x1, x2, x3. Then what does this thing means? We write down x prime as the identity goes as it is, dot x plus lambda. I transpose is just the outer product of the all one column vectors. So that's I transpose. And you again have x. Now, what I want you to realize that, where did I lost that stuff? Here. If you just do a simple matrix multiplication and stack up, you see the columns x1, x2 plus x3, x2, x1 plus x3. So you should convince yourself that if you change the labels 2 and 3 and keeping 1 fixed in x vector, then these elements have equal permutation. So a swap in the 2, 3 label is essentially swap in the 2, 3 label in the output vector itself. Do you see from this formula that if you keep 1 intact and change 2 and 3, then these 2 rows gets interchanged? Okay. So this tells you if you make a construction like this, then by construction, this layer is permutation equivariant on sets. It just now, if you again further split up and do a little algebra, you will see there is a piece which is the vector itself, and then there is another piece where it's the vector, and each element you subtract something by pooling. Now, here I have written sum of x, which is a sum pooling. You could have replaced it by any other function alpha x, which is invariant under permutation. The important part is that whatever you are subtracting here has to be invariant under permutation. And if this form holds, then it's a correct candidate for a permutation equivariant layer. Okay, this layer is something called, we will call a deep set layer. And when we build a deep set model, we will stack these layers up. Now, someone of you should tell me, given that gamma and lambda, if we convert it into some trainable parameters, is this layer a linear layer or not? Just from the mathematical expressions. What is the definition of a linear layer? Just scribble on your pen and paper that remember what was linear function on alpha x1 plus beta x2 should be alpha times fx1 plus beta times fx2. Do you see something like that similarly happening here or not? Sorry? No, alpha is, take it as sum or max, whatever, but it's just a constant number which is permutation invariant but is associated with the set. Anyone give a 10 seconds thought? It's a linear layer. So it's a bit non-trivial way to represent this, but this is a permutation equivariant layer which is also linear. Right? You should convince that by writing explicitly this on your pen and paper. So now it comes that we have to code this up. Now it's just a mathematical expression. How do we represent this in the code? And here it will come. So try to follow this code snippet with the formula. It's important. Where things are happening, that Yes. Oh. Sorry, can you repeat? Oh, this is to explicitly make it permutation equivariant by construction. That's the thing I emphasize, that if you write it in this form, then by construction, if you give a permutation on these three elements, the same permutation will be propagated to the output, right? So this is the way to construct a permutation equivariant layer. And if you read the Deepset paper, they will just point you to this formula. But it's good to do little two steps algebra just to realize it yourself. So I put it in the notebook. Okay. Yeah. I think if you take a linear permutation equivariant function, this is like the most general expression. Okay. Now, the later we will see that even if you elevate lambda and gamma to nonlinear multilayer perceptron blocks, the permutation equivariance will still hold by construction. Okay. But yeah, okay. No, ultimately, when we will make it nonlinear, we have to insert nonlinear activation layers. Okay, that's always you would do for a deep neural network. But it's good to keep track that in a deep neural network, when you stack different layers, which parts are linear and which parts are nonlinear. So we made the simplest possible choice to make a linear permutation equivariant layer, and then we will stack nonlinearity on top of this to make a full nonlinear layer. Okay. So the important part is how do we code it up? In PyTorch, all the neural network pieces are inherited from a class called nn.module. This I explained in details when I gave the online tutorial. And the forward computation, the feed forward operation happens inside something called the forward function. Okay, so whatever you're doing, it's happening inside this forward function. So X by construction should be a mini batch, which should have a shape of batch size. This N represents the number of points in that set, and C represents the dimension of the feature. Okay, and here you can do two different kind of pooling operation. I mean, you can do anything else. For the simplicity, I have kept mean and max. And you should see the same function, which was gamma dot x plus lambda dot something x minus something. I have kept this part, that you take it into an x and you do self gamma dot x plus self lambda x minus. You can x dot sum, x dot mean, whatever. It has to be just a permutation invariant alpha x. And the rest should be trivial. If you initiate a batch normalization, it will do a batch normalization 1D. And here gamma and lambda are just a linear layer, which means it's just like a metric multiplication plus a bias. And the rest of the thing should be same as this function. So let's take a break for 10 seconds and let's make sure that the function which was like from elementary algebra, it was obvious that permutation equivariant linear stuff, you can associate the same thing here. If there is any problem here in understanding. So we have defined nn dot linear. So the syntax is that when you defined basic layers in PyTorch in this way, these have the trainable weight parameters. Defining in this way will ensure that whatever weight parameters coming here, they will be updated when you do the backpropagation. But otherwise, it's the same thing as here. Yeah. I mean, let's say capital gamma. Let's look at the final algebraic, right?
To begin with, that capital gamma is like a diagonal
No. It's just a matrix with random initialization. If you want to put it as a
random, I mean to say diagonal in the x1, x2, x3, that direction. if it is not diagonal with equal weight, you need to have a permutation in that.
Initially when I wrote it, this one had like it was real numbers. Yeah. Okay, and then I'm elevating it to level of layers, and yeah, you have to first probably initiate with same diagonal elements. Yeah. Okay, and then you can do the back propagation of the training. Yeah, so you have to have an extra piece where you have to force that structure inside these weight parameters.
If I want it to remain permutation, want that
equivariant. Yeah. It will still happen here. You will see. Yeah. And then, so if you're doing a code, you ensure that the initial data chunk which we prepared, it had three features. It had two XY coordinates and the label. So each point had three features. And now let's say on each node, we want to create latent space structure, which will have 4 dimensions. So you can just create a deep set layer by this thing, and you can pass the point cloud chunk, and you can see that the output has changed to the feature dimension 4. You can interactively do it inside the code. Okay. Sorry? Which value? Right. No, here the initial point cloud had 3 features sitting on each node. Now it's a hyper, like it's a latent space. Okay, there you can have any number of features sitting on the point cloud. And if you set it to be 4, then it's just a demonstration that indeed after passing it to through a deep set layer, the number of features is turning into 4, from 3 to 4. Value. Sorry, that's a misstatement. Okay, but the important thing is you should realize that given an unordered set, this kind of construction will convert the number of points times 3-dimensional features into same number of points times 4-dimensional features. Okay. And now what we will do is to make a deep neural network by stacking up few deep set layers and insert nonlinear activations. So what we did is that first layer was a deep set layer here, and then we stacked a bunch of ReLUs and deep set layers one after another. And this is the notation. So what we are doing is that there was some input features, and then there was a list of features which will define what is the depth of the network. We will see it through code. And then if you're doing a classification task, probably you have to supply how many number of class you're predicting. For a MNIST digit, it's 10, like 0 to 9. And that's it. You can also specify what kind of pooling you're doing. You can do some pooling, average pooling, max pooling, this kind of thing. You have to pass that by a string. And what all you're doing is that you create an empty set of layers and keep appending the deep set layers and nonlinear ReLU one after another, so that now you know it's a nonlinear model because it's a stack of sequential stack of linear layers and nonlinear activation functions. You could have used one syntax that the whole layer could have been just nn.sequential. I intentionally kept it as something called nn.module list. You can Google it. What is the difference between a sequential and module list? You can type in the interactive cell of your notebook and keep that double question mark. Or after the talk, we can look it together. The advantage I see of a module list is that it's easier to access the output of each and individual layers. using the module list syntax in contrast to the sequential. So if you want really to access that what are the each and every stage of latent space feature update, then module list is a better way to do that. Okay. And finally, since we plan to do a classification task, we just take an output by doing a activation of log softmax. So that's what it's doing. So you have a bunch of deep neural networks, a bunch of layers. It had given an output. You know what you're predicting is a probability. So it should sum up to 1. So you finally taking the output after passing it through an activation of log softmax. Sorry? Oh, it's just initiating the constructor. This is a class and it has a constructor. That's the syntax. The rest is kind of trivial, that given that we have defined the model, you see, we now write a deep set model which had 3 input feature parameters. And here features, you can give arbitrary list of integers. The length of the features kind of list will be the depth of your neural network. The more you give this list, the more number of layers will be appended. And these are the dimensions of the latent space features of this point cloud. So it will start from a 3, will go to 5, 9, 12, probably 16, 13, and it will come down to 10. And then you do an active, like softmax activation on 10 different features, and you know those are the probabilities for belonging to the 10 different class, which are the classes of the handwritten digits. But this concept is same for when you did the MNIST classification previously as well. Okay. The rest part is kind of trivial. Like I personally prefer to just load one chunk of data set to the whole model and see the output is coming sensible. So my batch size was 5. Okay. And my output is something like that, and label size was 5 different integers. So if you had 5 images to start with, you should have 5 different integers. You can compute a NLL loss, and the most important part to check is that the loss function has a right gradient function. If you see a loss function doesn't have a gradient function, you know something is surely lost, because there won't be any backpropagation on that loss if there is no valid gradient function. Okay, so keep this in mind. The rest of the part of this code is kind of trivial, that we create a training batch. And here you see that after each chunk of the batch, we do compute a loss on that mini batch, do a backpropagation, make one instance of optimizer stepping where this computation happens, and we update the weights. Okay. And similarly, we can test the model on a validation set where no backpropagation happens. So we just create a test batch. And then nothing very conceptually deep here to say. It's you can see the syntaxes here, how to take one big data set and split up in training, testing, and validation. This subset random sampler is the way to do it in PyTorch, but conceptually it's similar things you do in TensorFlow, JAX, whatever is your favorite library. And just to remember that when you create a training loader, test and validation loader, you pass this batch and the right sampler. And then you can define an optimizer. You can use your favorite. I just put stochastic gradient descent. In this, I can explain during that first online tutorial that the optimizer should get all the trainable parameters. Otherwise, if you don't pass whatever parameters won't be passed through the optimizer, it won't be updated. So it's important to keep this thing in mind. Okay, and then you run a training loop. Like this should work out of the box. You see which is the best safe model. I did it like on my computer for 20 epochs, loaded the model again, and just evaluate it. So just a very short training on a chunk of MNIST data set will give you something like 90%. But that factor is not important. How many percent is the accuracy? Conceptually, what we were trying to do is to what you were familiar with. You did image classifications before. We took the same images, converted into a set data set, a point cloud data set. And we learned how to write a permutation equivariant layer, which will act on a set, build a deep neural network model, which is a stack of those permutation equivariant layer and nonlinear activations. Okay. And then through some mean pooling or something, or some pooling, we converted this set to one particular number, which should give you the probability of this set to be for some integer. And then we did a statistical learning task for like training, doing the right back propagation, updating the weights, and finally for the best safe model, which we believe should capture the general features of the dataset as a whole. On an independent test dataset, we evaluated the performance. So we did one set of whole possible tasks which you do when you do a machine learning task, but on a very simple toy dataset, and I tried to demonstrate you the steps. So take 3-4 minutes, go through the code of your own, and at any step, the flow which I said you, that what are the possible steps we wanted to do. If any step is not clear in your mind, not each line of code, but as a whole, what each different parts of the code is doing, then please raise the issue here right now. It's important that we haven't done any serious graph learning or anything. We just converted an image to a set and tried to perform one task which you do in your very first machine learning training. So tell me if there is something conceptually missing. Let's see. Num workers. Oh, that's because that parameter tells you how many parallel GPU to which you should spread your work. But here on my computer, I just running on one machine, so I set it to 0. Number of? No. We did. You can do in PyTorch. There is a structure called data parallel through which you can parallelize your job. But since I did it only on my computer, I didn't parallelize it. That's doable. When you load the data loader, you can make the custom set in and wrap it through a class called data parallel, and then pass it to the data loader, and it will take. What I will not discuss here, at least I don't plan to, is to how to do something a training in PyTorch Lightning, and that's a very efficient wrapper. And if there are multiple GPUs and parallel computers available, it does all this for you, and you don't need to need as an end user to worry about all this. If you are interested, we can take it up in one of the evening sessions how to do that. But I wanted to make sure the bigger picture is clear rather than this individual hardware acceleration points. Point cloud data? Okay, so let's go back to this image. we had an image here. It was 28 cross 28 pixels. Lots of the pixels just had 0 value. So when you applied a convolutional neural network on this data set, the filters learned where the edge of this image is. Like some are 0, some are non-zero. So that helped a kernel function, a convolutional kernel, to determine the age of these images. But you have to use a lot of zero values to make this computation happen. We want to ensure in this treatment that are the all possible non-zero values are important, or we can just use where the non-zero values are and what are the non-zero values itself, because that's how we showed that if you can specify the location of the non-zero values and the value, you can build up an equivalent data representation, which was this 9. So this is just a point cloud where you know the locations in a 2D plane, and you can also put values on each of the points, and this data should have similar meaning to a general handwritten data with lots of zero elements. Now this is less byte of data compared to the previous image, because you have thrown away the zeros. So this should be computationally more efficient. Okay, and now this was one purpose. The other purpose is just to demonstrate you how to do machine learning on sets, because not everything will be toy examples of images and handwritten digits. There can be sets of objects interesting in real life, but how to write a neural network on a set. But the concept of a permutation equivariant layer, which you learned here, the same concept should pass through on the sets. Okay, so this example was picked up because I expected everyone has done some image classification. So just converting the data structure you know into a set and then doing machine learning on sets. Okay, so that was the idea of introducing deep sets. Right. X dot mean. So here you see that it clearly tells you that average over the points. So before that, the whole set, all the individual nodes were accessed. But then this collection of points should map to one value. Here you want to infer what digit it corresponds to. So that's an unique level. So you have to gather the information from all the value, map it to one feature vector, and then infer on that feature vector. So that's why, I mean, you could have done any permutation invariant pooling operation here. It should work. That was in different part, no? So you see here that first you're doing a backpropagation on individual batches. And then you compute in the training loop, you sum the losses, right? And this sum is from all the mini batches, because the train loss, which this loss function returned, it was a sum over all the mini batches. Okay, and you stored the state of the training based on that total sum. So the total data set was used, the loss on the total data set was used to decide whether this particular training epoch will be stored as a best fit or not.
This question was regarding the linear layers in the weight within the x equal to layer x. Because you are
X equal to layer x, it's just, let me first confirm that was the question.
when you're saying you meant the weight is within the layer.
Oh, but when you're doing the backpropagation, if a full model is built out of several intermediate layers, all the weight parameters are changed through backpropagation steps. So when I said W prime equal to W minus del LW, this W consists of all the weights sitting in one deep neural network. And this means the weights coming from all the layers. Okay, so when you saw the loss function has a gradient, active gradient function, it means that the loss is a function of all the trainable parameters in the model. Yes, when you do a backward, all these parameters are changed simultaneously. So when you do optimizer.step, this step is changing all the parameters at one go. Right. And the output is just, what is the output? It's the probability of each class. So in general, when you predict, there won't be a single prediction. It will predict probability of belonging to all different classes. And then you do a NLL loss to say which class this loss is closer to. So it's a yes, exactly. Because your last layer gave you the vector which has 10 numbers, and that you are comparing with one target. And these 10 numbers are 10 different probabilities, and with each probability you see what is the target, and you tell the network to which it is closest to. Right. There is no unique definition of loss function. You can do any loss function, but it has to be like serve your purpose is that when it's closer to the label, the distance is closer. There's no unique prescription. Right. So in this is kind of a pointer, but not exactly in the sense of C++. The notion is that when you see when you wrap it in the sequential, the star layers is like giving you sort of a pointer of that all that array, and the module list treats them as different elements of that array. Okay, so this is like the syntax you use. But if you used either of the two, the self.sequential will be the same function. It's just that the module list allows you to access all the outputs individually, whereas if you use the sequential, then you get the whole output at one step. You could do either or according to your test. I prefer to keep it in a way where I can access the output of each layer in case I want to look at them, want to have an access to them. So that's why I kept it this way. How long this session will go?
12:30 is
12:30. Okay. Sure. Right. And the label, the pixel value. Right. Whatever you decide. The 5 features is some latent space feature, and they needn't have any physical interpretable meaning. It's just some updated representation of each and every node. When we wrote down this deep set model, you saw we had 13 dimension, 12 dimension. Do we need a human interpretable meaning of each of those 13 numbers? No. It's just making it deep and making more number of parameters is just increases the expressibility of the neural network. I hate that neuron picture. I always think it in terms of layers, and each layer has their own width. So the making that number higher means making the number of trainable parameters from each layer higher. Yeah. Right. So if you are satisfied that what was done here is okay to you, then we will go to a jet and make a set representation of a jet. So I need a green signal from you before I move to that example, that you got the basic picture right. Can we move on? Okay. Because the next example, what we will do is something similar, but instead this was a toy data of image. Now we will start dealing with jets, some real high energy physics example. Okay, so again, in the GitHub day one, you will find this piece of code that jet, deepset, something, like, and here it will be important to give a bit more emphasis on the data itself, because when you will solve the problem today post lunch, you have to use some data loader like this. So make sure you follow me. So I'm starting, okay. So the first thing, the data set which we are using, this is like, I don't know, 15, 20 MB data from this public website by Huel and Q. And I posted this data set like, I think last Thursday or something. So probably good if you download it. Also, you need this library called uproot, and this allows you to read root files without having root installed in your computer. It's pretty handy library. There's no point in installing a heavy library like root unless you're really going to the source codes and things like that. So before doing any machine learning, we need to understand what are the kind of feature variables accessible here. So how many of you have no idea what a jet is? You can raise hands. Okay, couple of you. We will discuss later, but for this discussion, you can think of them. It's a set of 4 vectors. Each particle should have a 4 vector, this you know, and a jet is a particular set of such 4 vectors. Keep this picture in mind, and this is sufficient for this discussion. Now, each particle have different kind of properties which we will use. So let me, for your intuition, let's just draw a jet. It's kind of conical kind of shape where you know there was an initial parton which underwent parton shower. Then there was some fragmentation and hadronization process, and finally you have a bunch of hadrons which are stable particles which we observe, and this is a picture in the eta phi plane or whatever, and this is what we call jet. And we now need to understand what are the properties which we can associate with each of these elements, which will called features of the particle, and as a whole the jet should have some properties. Okay, so that we will call jet pt, jet eta, things like that. And there is a jet axis which is like this. Okay, so just to understand what these variables are, when you in the list you see something like say d eta d phi, it means that the jet along this central arrow had an eta and phi, and the difference of the eta of the particle with the jet eta, that's what is called as d eta. Does this make sense? Similarly for d phi. So the jet had some kinematic core momentum of its own, and each of the individual particle has their own kinematic features, and the difference between the relative location of the particles with respect to the jet. So if this is your central axis, where do the particles lie compared to the central axis? That's what those variables are. And these are interesting variables which have physics information hidden inside it. Okay. Similarly, this jet has some labels. So this jet itself can be like Higgs decaying to a BB bar pair, which is labeled as HBB. It can be a Higgs decaying to a CC. It can be QCD, which means a gluon decaying to BB bar or just a gluon jet, and some other features. So this is something like a discrete label, just like the digits of MNIST 0 to 10. This label can have this, how many? 7, 8 labels. You have jet properties, the kinematic properties, number of particles inside jet, okay? That's a number which will require. And then there is something called jet tau 1, tau 2. So if you know jet substructure, if you have studied something called n subjettiness, these are interesting feature which tells you what are the pronginess of a jet. If you have never heard about this thing, just deal them as some feature of the jet, and you needn't worry about the physics for the time being. Right? So you can just use the string like the star symbol to browse what are the subset of variables with that particular name, and that should suffice. So first of all, what defines a jet? What are the constituents, and roughly what are the meaning of these features? Do you have any questions? It's good to have a feeling about. Then the tree variable is not properly defined in your case. The tree should be something like uproot.open.
Equal to part underscore star. So I think this is using some old uproot. So
Okay, maybe.
yeah. So in new uproot, you will have to put filter underscore name equal to and then this.
So that's a key variable you need to use, yeah, to filtering. Yeah, probably uproot has updated to version 5, and I'm still using 4. So maybe I will fix that part, but nothing else should change. It's just a browse at the opening of the root files. Any other question about the feature variables? Good. Okay. So later you can browse all the individual things of your own, and it should be fun to look into. Just to give you another example is that I kept these little pieces of code snippets just to read individual branches and arrays. They don't have anything to do with the machine learning tasks we are going to solve. But if you want to browse the individual branches and how do you do that, how do you convert into NumPy arrays, what are the number of particles inside a jet, things like that. Okay, it's not that important. And whether you're doing anything sensible or not, how do you see that? So SD mass is something called soft drop mass. You can access them. You can filter the arrays by either HBB and top jet. So there should be a jet which is coming from a Higgs decay versus there should be a jet coming from a hadronic decay of top. And if you plot the masses, the soft drop masses of those two jets, you can see one is peaking around 125, another is peaking around 173. So the labels do make sense. and whatever labels were there, they were indeed coming from Higgs and indeed coming from top. So you can just browse, filter them out, play with them, plot the properties of your own, can try to plot the individual properties of the particles coming from one set of jets, and you have little code snippets to play with this root file. Okay, now the important part. We need to form the point cloud on the jet. So earlier in the example, we converted one 2D image into jet, 2D image into point cloud. Now we are going to make the jet, whatever data were present there, into a point cloud. So we need to understand how to do it. So please pay attention to this function that transform jet to point cloud. What did we do? We first took out jet pt eta phi energy, and like tau 21, tau 32 are just the ratio of tau 2 over tau 1. Tau 32 is ratio of tau 3 over tau 2. They have interesting physics meanings. We can discuss in evening what do they mean, but for the time being, take it for take them at the face value. Okay. Now you should the real thing you should see is that particle feature are the individual feature of the particles which we browsed, and we accessed all of them through this one line of code, that whatever were the particle features, they were something called awkward array, because there is a variable length size in the number of particles in the different jets, just like different numbers of points in 9 versus different numbers of points in 3. Similarly, each jet have different number of constituents. So inside the root, they are stored as awkward array, and that's the way to read awkward array. And we have all the interesting particle features. So this is a NumPy array, and we just stack them. So this line is what makes earlier when you had the point cloud for an image, it was number of points times 3. So here that line will convert, it's the number of particles times the number of feature of the particles. Similar things, exactly the same thing what we did for image, now we are doing with the particles inside a jet. And finally, we make total jet feature is that we stack the global features of the jet with individual particle features. So we just increase the number of feature dimensions for each particle. So we copy the total jet feature to each particle. And that's what we do by putting this line that NumPy concatenate, and that's it. And we keep a check that through this division process, if there were some zero division, we just remove the NaN parts and convert them to 0.
Jet PT as well as the information
Right,
about the
right. Well, for this example, we copied the jet to the particle, jet information to the particle. Later, you will do some exercise where we will, in a graph, we will keep the jet data as a global data and individual particle data as node data, and you will do some GNN with that later, but not today. I'm walking through this example in detail because for all the examples, this is the data set which we are going to use. So better have an understanding what the features they are carrying and how to play with them. Okay. Right. And now, as far as the label goes, based on the string, you can figure out which classes belong to. Like I have labeled the QCD as 0, then Higgs class as 1, and Z or W as 2, and the top as 3. So it's kind of a 4-class classification. You can convert it into a regression problem as well, where probably today only, instead of a classification, you can do a regression in the exercise which you will do. Okay. And for each jet, then we just return the jet features, like all the particle features, the label, again the sequence length. And I have also added the soft drop mass as one of the data returning. So you can later in an exercise try to see if the particles of a jet given without running the soft drop mass, can you regress the soft drop mass? If you want to perform this kind of exercise, that you want to replace the soft drop algorithm by a neural network, it's good to have this as an output so that you can use the number, all the particles as the input data X, and make this as your target. So you can play with this kind of stuff, right? And the rest of the stuff, length and get item, you know what it's doing. Fine. The create batch function, which we told you, here, since we are not using PyTorch geometric, I have to make a create batch explicitly. Later, when we will use that library, you will see you don't need to keep track of this creating batch by hand. The library will take care of itself. But since for the first few times, it's good to do it explicitly of your own so that you know what exactly you're doing. So I find that helpful. So this is again a few different jets. You're forming a mini batch. Each jet has different number of particles. How to stack them, all the particles together to form a mini batch. You're getting the jet level. You already had like max length of the sequence, which was the 0 padding. And then you are filling up the rest of the vectors. And similarly, what we did before, we are doing the same here. Just to keep one thing in mind, that the data set had the soft drop mass. We were returning the soft drop mass as a part of data set. But in the create batch function, we didn't use that at all. So when we will iter over the instances of our data loader, that won't have any soft drop mass. For this example, it will just return the set and the label. But for exercise, when you will try to regress the soft drop mass, you have to modify this function to build an understanding of what this function is doing. You have to include that soft drop mass and put that as one of your targets. So it will be a good like hands-on exercise to play, that you just change the data loader outputs and reshuffle your statistical learning task in an equivalent fashion, right? Okay, so the rest of the part of the code is exactly same, because all the physics were going into like into building the data set and the data loader where you injected your physics knowledge, etc. But the rest of the stuff, how we build a deep set model, how do we train on a set, that's universal. And once you have learned that, you don't need to change that part, whether you're doing a point cloud on images or point cloud on the jet data set. So it's exactly the same thing. So you see that you will find I'm using the same Deepsets, but just appended inside some module. Probably I forgot to push the modules in the GitHub. I will do it, but this Deepset is exactly the same function as here, exactly the same thing. And we keep checking that everything is fine, that what's the output is coming and what's the level, and then we perform the training. The rest of the part is just same as you did in the previous exercise. So this is just to highlight that once you know how to write universal functions on sets, it doesn't matter whether you're doing images to point clouds and doing some statistical learning task, or data coming out of some MATLAB Delphi simulation to form jets, and you want to do a classification or regression. The point of writing permutation equivariant universal approximator remains the same, and you can perform the same task. So that's the good part about it, that once you learn the general mathematical concepts, that how to learn, define neural networks on sets, you can apply it on any kind of data sets of your choice. Okay, and you can do deep sets training on whatever set-based data set you want. So now you can bring any other set data set, say from biology or from cosmological data, the same thing will work there as well, because while you were formulating the permutation equivariance set functions, you never assumed any particular property about the physical data set. It's just a mathematical construction. And yeah, so hopefully we will have fun during the hands-on tutorial session post lunch, and then there will be another session after the hands-on tutorial where you will learn basic introduction to graphs and how to do some elementary presentation and coding on graph. And let's see. And in between, if you have questions, comments, we will be happy to take them. Okay, so let's take a stop here.